Cloud. We're recording. So Jordan, welcome and thanks for being here.
Yeah, thanks for having me. It's always fun.
Yeah. So Jordan, did I do correct service on sort of your introduction? Is there anything else that we need to know about you? And by the way, I put your LinkedIn on the Trello card for today, so so that's there in case you get a lot of friend requests from this little exercise.
You're more than welcome to look. I will tell you that I only connect with people that I actually know personally, so I'm probably not going to accept anyone's, but you're more than welcome to look.
Okay.
Yeah, that was a good assessment. You knew because you were there for all of it. He was also, I don't remember the name for it now, but you were one of the people on my board for my master's thesis too.
Yeah, that was a fun trip. Thanks for that.
Thanks for participating. Yeah, the only other thing that I will add to that right off the bat is maybe not everyone knows what JPL is. So JPL is the NASA Jet Propulsion Laboratory in Pasadena, down in the LA area. So all the different NASA facilities specialize in different things. So you've heard Houston, we have a problem. That's because Houston, Texas, the Johnson Space Center, that's where the astronaut corps is. They run the human spaceflight program out of there. Cape Canaveral, or not Cape Canaveral, but the Kennedy Space Center down in Florida, that's where they launch rockets. Huntsville, Alabama, the Marshall Space Center is where Spaceflight Center is where they design a lot of the rockets. So JPL specifically is the robotic exploration arm of NASA. Our job is to do robotic exploration of the solar system. So we're probably most famous these days for the Mars rovers. We also did the Voyager spacecraft that have left the solar system. We have a ton of Earth science spacecraft in orbit around the Earth doing research on climate change and soil moisture to help our farmers be more efficient with their farming. We've explored every planet and we just keep going and going. We do space telescopes. We want to send our little robot emissaries out there to explore on our behalf because humans can't go quite everywhere just yet.
Yeah. Well, Jordan, this super interesting stuff. And but can you talk a little bit about, like, what's lean about your job? So quality assurance engineer is sort of traditionally that's always sort of existed in one way, shape, or form in organizations like JPL. But have you been able to bring some sort of lean perspective into that, or some insights?
Yeah, for sure. So so quality at JPL is pretty different from how it is at a normal company. And I know Dr. Olsen always likes this part because it's kind of amusing. So one thing about JPL is that we basically only ever make something once. Every single spacecraft is unique. It's always custom designed. Even so, like this picture behind me is Curiosity, the Perseverance rover that we landed earlier this year, which was incredible, and I hope you watched it. It looks pretty similar, but we actually had to redesign a whole bunch of stuff for it. So it used basically the same landing system. It used a bunch of the same stuff, but it had a whole new set of scientific instruments on it because we're trying to answer new questions. We're not going to send the same thing twice. We already did that. We want to learn something new. All of those are different power concerns. So now it has a bigger power source on it. Well, the bigger power source requires a different system, and you need the heavier wheels. You need the bigger, and just all these slight changes, even when they look the same, every single one is basically different. Every single one is unique. Which makes Lean Six Sigma really weird, because usually when you are looking at like PepsiCo, for example, or Procter and Gamble, or what have you, they're doing like 1 million cans a day, or I'm making that number up. Maybe they're even bigger than that at this point. You're doing a lot more statistics on that. We in QA at JPL, we effectively don't do statistics, because what statistics are you going to do of n equals 1? We're just going to do 100% inspection instead and make sure that each one is good. The other thing is that we deal with lots and lots and lots of unknowns, and there's no way for us to fix it down the road. So we like to say there's no tow trucks on Mars, right? If you're driving your Ford along on Earth and only on Earth, we're not launching Fords yet. Well, SpaceX launched Tesla. Anyway, if you're driving your Ford along and you have something break, you take your mechanic. I went to my mechanic this morning, right? It's not the worst thing ever. You can call AAA, it's okay. For us, if we have one ball bearing get stuck, and the wheel stopped turning on the rover, your rover has now turned into a very expensive lander. And you can do lots of great stuff, but there's nothing we can do to fix it. It's just the way it is now. You can fix software artifact, you can't fix hardware. So it's a very high consequence. Some of these can be very expensive missions. One of the missions I'm working on right now costs $4 billion. We really don't want it to fail. And it's going to an environment in Jupiter that we've never really been in before. And thus guaranteed there's going to be things that we just can't plan for. And so we have to make the best risk assessment we can. I'm going to detail, I always do. Basically what I'm trying to say is two of the things that make JPL different is that everything is unique, so you can't do the normal statistics on it. And there's always a lot of unknowns. And so a lot of our job is actually risk assessment. So I'm not just implementing things on the floor. I'm not just, that's part of my job, but I do a lot of risk assessments. We are actually considered engineers. I have a master's degree in engineering.
So Jordan, just trying to tie that into the class. Yeah. So well, no, but last week these guys just learned about FMEAs, and you were talking about you had a sort of a big discussion, I guess, just last week or something about that, right?
Yeah. So we had this in a meeting last week. So one of the things that a lot of what we do comes down to risk assessments, right? We never ever launch something with zero risk, which is really weird for us in QA. We always launch something that has a slight chance of completely failing. Because if we're not, then we're not pushing ourselves hard enough. We're not trying something new enough. We could be trying harder. We could be doing something more adventurous. So one of the things that a big part of that is discussions around, okay, what level of risk is acceptable and which types of risk. And I'm not going to get too deep into it unless Dr. Olsen asks me to, because I can go on this forever. But the specific discussion he was talking about was last week I was in a meeting where we were talking about, okay, for this one thing, we were just trying to figure out which analysis to even do to determine determine the level of risk that would be appropriate for this. Would we do an FMEA or a FMICA? It's you add a C in there for criticality. And the reason that we were having this discussion was not just to be obnoxious. It was because actually defining for each failure mode what the criticality was of it was a lot of extra work. You're taking it from.
So what's criticality? So you got severity. That seems like criticality. Those seems like the same thing. Is it different? So usually FMEA severity, detectability, and frequency, right, are the three. And then you added criticality? Is that? Yeah,
so honestly, I wasn't the one doing the analysis. That was a reliability group. I'm not entirely sure what they're doing differently.
Okay. But there's something different about that, I guess.
Yeah, there's more in depth you have to do with it, because you have to start trying to actually define things and trying to measure things and trying to actually figure out what is the criticality of this goes wrong. What are all the things related to it? The point of me bringing that up was not to teach a specific tool, because I'm not the right person to teach that, and I probably should know that better, honestly, but was to say that we put a lot of effort into planning, lots and lots and lots of effort into planning, because you only get one shot. And even when you put an incredible amount of effort into planning, there's always going to be what's often referred to in the aerospace industry as unknown unknowns, the things you never ever could have planned for. So very short story on this. The InSight Mars lander, it landed a few years ago. It had two main instruments on it. It had the seismometer that was built by France, and the heat flow probe that was going to dig down and try to figure out how hot it was inside Mars, so we can learn more about the inside of Mars, because we've only ever looked at the outside of Mars. Those are the two main instruments. When we went to launch, the launch actually had to be delayed by 2 years because there was manufacturing problems with the seismometer. We were able to detect that because it couldn't keep a vacuum seal while it was on Earth. It was a pain in the butt. It was real expensive to store it for 2 years. It was really difficult to do, but we were able to find the problem and we could fix it. And the seismometer is doing great. We've now detected a bunch of Mars quakes. They're not earthquakes because they're on Mars. The heat flow probe, on the other hand, was built flawlessly. They did there's always problems, but they did a great job on it. Germany knows their stuff when it comes to engineering, right? And it gets to Mars and it starts trying to dig down. And over the course of 2 years, they failed to dig into the surface. There was nothing built wrong about it. They built everything the way they were supposed to. They designed it to the best of their knowledge the way they could. What had happened was we had landed on Mars, I don't know, half a dozen times, maybe more. I don't remember the exact number, maybe 9 times before that, in various places all over the planet. And we thought we had a pretty good understanding of what Martian soil was like. And it turns out we had a pretty good idea of what Martian soil like everywhere but where it landed. And where it landed, the soil just had different properties, and it physically wasn't designed to drill into that. There was no way we could have known until we landed there, because you just don't know what the soil's like until you get there. There's nothing we could have done differently. And I would call that a successful failure. They did everything right, and it just didn't work because we were in a risky business. So we always have those unknown unknowns. We always have the risks. So it's just a matter of when we talk about what's an acceptable level of risk and what types of risk, those are all the discussions we're having. And you have lots of people try to agree on it because they're hard decisions to make and they're always made with imperfect information. I don't know how much that applies back to lean, but I like talking about it.
Hey, Jordan, I want to swing back a little bit to the, the discussion about, one of the things at JPL, N is equal to 1 or N is usually real small, right? So you don't have that statistical sample. And I mentioned that, one of the people, so Jim Morgan wrote a book called Design for the Future and has been really looking at, well, how does lean apply in, knowledge or research, type environments, right? That, or R&D type environments. So maybe that's a little more akin to where you work. And so what he's trying to do is trying to tout the idea it's about knowledge rework or not rework, knowledge reuse. So if you learn how to do something, like say you learned how to do this criticality FMEA or whatever, you sort of nail that down so that, the next time that situation comes up, you could reuse not necessarily the same thing, but you're applying that knowledge, in a different way, but it's reusing the knowledge. Do you see like instances where that kind of concept could be helpful or useful for you?
Yeah, and I realize I totally dodged your earlier question about how it was actually different. So I can come back to that if you want. Please remind me because I get distracted. So the knowledge is a huge thing for us. So for example, one of the biggest missions that I'm currently working on is Europa Clipper. It's our next mission to Jupiter. It's this massive, hugely complex program or project with lots of different partners from across the country. It's going to be doing some amazing work. In terms of Jupiter orbiters, this is going to be our third ever. In terms of Jupiter, we're actually really fortunate. The last one is very recent. It's still in orbit. Juno is still orbiting around Jupiter. Galileo was back in the 90s, early 2000s. The problem that runs into that is, so I'm in my mid-20s, right? The last time we built a Jupiter orbiter, I was still in, what was that? High school, I think. And the last time before that was, I think, shortly after I was born, maybe a little bit before I was born, right? And now I'm part of this team building this Jupiter orbiter. And we want to incorporate all the lessons that we've learned over time. But I don't know those. I wasn't there, right? We have such long lead times. It can take 10 years to design and build a project. And then it's going to take like 7 years to get to Jupiter after we launch it. And then it's going to start doing its science. It's not launching until 2024. So we have these such long lead times and such times between it that knowledge transfer and knowledge reuse is a massive issue for us. So a lot of times people look at JPL or NASA in general, and they look at the red tape and they look at the bureaucracy. There's absolutely a lot of bureaucracy at NASA, and one of the reasons I love doing lean at NASA is trying to cut a lot of that down. But I would never want to go to zero, because within that bureaucracy, within that red tape, is a lot of really important procedures that are our value. The way that we capture lesson learns over time is we build them into our rules and requirements and procedures, right? Because you can't depend on someone sticking around for 40 years. We have lots of people who stick around for 40 years, but you can't depend on everyone sticking around for 40 years, and they might be on a different project. So what we do is we change the ways that we do things in our rules, and then you follow the rules. And that we capture it all into our documentation in that way, into our processes that way. And sometimes it feels weird that you're saying, oh, my job is to make sure people follow the processes. What we're really saying is, my job is to make sure that we do everything the best way we know how. And since there's so many thousands of people working on this over so many decades, this is the only way we can have a common language to actually go work through it all.
Interesting. Hey, so Jordan, I want to make sure that the MBAs that are sort of in this class, we're open for questions. I can go on for a while. I know Jordan can go on for a while on this. We can get pretty geeky if left to our own devices. But if you got a question, go ahead and type it in the chat. I'll make sure that Chris, if you can sort of flag me if there's something in there that needs to be asked or whatnot, that would be good. So another thing that we're going to be embarking on this week, well, let's see. So two topics for this week: 5S, and then also single minute exchange of die or quick changeover. So I was thinking a little bit more about sort of the n equals 1. You know, in a lot of ways, when we're talking about setup reduction, you're all set up, right? So you set up for 5 minutes of the rover on the surface, or you know, even when it's, you know, longer, I guess, you know, there's just like years of setup, and then the actual run or the value added piece is when that rocket blasts off, maybe, or something, right?
Yeah. So we don't do SMED in the way that you would in a normal assembly line because we don't have any automated assembly. Because every spacecraft is unique, and because we have such very exacting requirements. No, because every spacecraft's unique. Intel has exacting requirements. Because you never do it the same way twice, there's no real way to automate it. So we still have humans assembling everything in the clean room. You know, like I've held in my hands some of the parts that are on Perseverance on Mars right now. And so you always have to deal with the human in the system. We don't have a big die changing out in an assembly line because there's no assembly line. However, there is the human assembly line, right? So there's certain things that are very repeated, and there's certain things that are totally not. And a lot of the art of applying lean at JPL is understanding how to tweak it to make it work for us. And the longer I'm there, the more I realize does fit, and the longer I'm there, the more I realize doesn't fit. It's kind of both, right? So Six Sigma applies a lot less. I haven't used a statistical process control chart since I was in Dr. Olsen's class because we're doing 100% inspection. You know, what are you going to do? You're only doing n equals 2. Maybe you'll do n equals 5. You're making some spares, right? It's not quite the same. However, we do a lot of lean, and we do some Six Sigma. So to give you two very contrasting examples, maybe. So we have the receiving inspection area, where they're taking in all the parts that come into JPL, and they're making sure that the suppliers basically gave us what they said they were going to give us, right? You said you were going to give us screws that have no tin in it because tin destroys spacecraft, fun fact. We're going to actually check and make sure that your screw doesn't have tin, that you didn't give us a counterfeit part, because that happens and it can destroy spacecraft. They're gonna go through all these screws. They just follow the inspection plan, right? They're doing really critical work. They do some difficult work, but they're not, they don't have to reinvent the wheel every single time. Whereas when you're trying to figure out, okay, here's the other extreme example. So most of our spacecraft run on solar power. It works great, it lasts a long time. It doesn't work in every environment though. So for example, the Perseverance rover runs on plutonium. So we install plutonium power sources very, very rarely. They're very difficult to do. We are very careful about doing it. We're very sparse about doing it. We do it very rarely. You're only going to install it once a decade, once every couple decades that we actually go ahead and do this. So we spend years planning the process for how you install the plutonium power source in the Perseverance rover. And then you spend half hour, you do it once, and then you leave because, you know, you get a lot of radiation for your employees. So there's no exchange of die happening there. There's no repetition there, but there's a lot of repetition that happens in receiving inspection. Or maybe a middle example would be mechanical inspection. That's our running our coordinate measurement machines, figuring out the exact dimensions of all the metal pieces that we cut out. Every metal piece is going to be different. So you're going to be writing a new program every single time for each one. But the process of get part, write program, inspect it is pretty similar from part to part. So you're not going to optimize it down to the second because you're not going to have the same program over and over. But the idea of the process flow and then optimizing and removing a lot of the waste in that process totally works. So there's ways it applies, there's ways it doesn't apply, and a lot of it is the art of QA. Did that answer the question obliquely?
Yeah, no, that's good. And I think, you know, if there's one thing that I would like the students to take away is, you know, some of you know, it's more about the thinking process, right? The asking the questions, the challenging, you know, is this the right way to do it? Is this value added or non-value added? If you could start to think about that in whatever situation they're working in, you know, I think that's sort of a big plus. Let's see, do we have any questions yet in the chat? If we do, we'll switch you over and you can ask those to Jordan directly. And I know you guys can come up with some good tough questions. Hey, Jordan, I'm switching topics. I'm thinking about some of the things that these guys have started to learn about and are trying to apply in their projects or whatnot. And they're required for their projects to do a value stream map, right? So you've heard about some HR processes and some processes with purchasing and whatnot. And I also know that you actually put out a call to maybe hire an intern or two or something to do some, was it value stream mapping, or is it some other kind of process mapping that you guys want to do or need to do?
Yeah, we are doing some process flow mapping this summer, and we do have an intern coming from Cal Poly, actually, from the ITP department. And they'll be trying to make sure that we tie a lot of our different sections together. So, QA is specifically working at one part of the puzzle, right? Like I said, there's a lot of different types of risk that we have to work through. We're specifically looking at the implementation risk. Did the thing that was on paper, your blueprint, actually equal what was physically in the real world in front of us? When you said, I'm going to run tests and this is success and this is failure, did you actually meet the criteria you set for yourself? Did it actually succeed or not? We're the second pair of eyes, because all this stuff is so complicated that even people who are the best in the world are going to make mistakes. Our machines are going to make mistakes, and we will just account for that, and it's totally okay. And that's what we're here for. But that's only one part of the puzzle. There's the reliability group that's trying to figure out, okay, but what was the soil that we need to, or the environments group that's like, okay, but what is the soil that you have to design for? And the reliability group of, okay, but what actually numerically is the likelihood that this computer chip is going to fail in the radiation environment at Jupiter, because the radiation there is obnoxiously insane and just ridiculous to deal with. And so we have to have all these groups talking together and actually integrating together. And so, for example, that meeting I had last week where we were arguing about, are we doing an FMEA or a FMICA? The reason that I don't know that tool as well is because that's the reliability group's job. And that meeting was actually working on some of our higher risk tolerance projects, figuring out how we can work together even better than we already do, to make sure that we're taking their assessments into account when we're figuring out which things are we okay accepting the risk on and which things are we not. And so we're always improving the way that we actually map our processes and start getting groups to talk to each other better, because we have all these incredible experts and sometimes they can get siloed. And it's a really important problem.
Yeah. So Jordan, what was somebody recognizing, boy, we should map this process, right? And maybe it's a swim lane diagram, or it's some sort of mapping to say, this is how these groups should communicate, or the process should flow. Was that a recognition that we need to do this because this doesn't exist, or is it because it exists, but the process is out of date and it was too linear, but we're going to be a little bit more parallel, a little more dynamic? Like, what's the mapping challenge, I guess, for you in this? Is this something can you actually map this stuff, or?
So for this project in particular, I don't know the exact specifics of it. I'm not the one leading the project. But I can tell you in general for us, one of our bigger emphasis. Okay, actually, this is a good one. So something that maybe this will apply a lot more to some of the MBAs, because you're not necessarily going to engineering, all of you. A lot of you are going into different businesses that aren't manufacturing things. Something that I deal with specifically, is we actually have a variety of different projects that have very different needs. And a big part of our job is making sure that we meet their needs in different ways. So for example, the Perseverance rover is massively complex. It's a huge international effort. So it's a big diplomatic thing if we have issues with it. It's really expensive. It's a really high priority. It's doing some of our most interesting, our highest priority science for the country. We have a very low risk tolerance on it. Still not zero, but for JPL at least, a low risk tolerance. The flip side of that is Perseverance had a hitchhiker that went with it. It had a helicopter that we sent to Mars that's now flown a few times, called Ingenuity. That one was a technology demonstration. That one had a very high, relative to Perseverance, not relative to a university, risk tolerance. It's only designed to last for about a month. It's already lasted for a month, so now it's surpassed all expectations. Anything beyond this is just icing on the cake. All it had to do basically was to fly once or twice, and it had met all of its qualifications. Everything else is bonus. So, and it's orders of magnitude cheaper. So it has very different needs. And so circling back around to what you're talking about, the process mapping, we're always looking at what are the actual needs we need to meet. So for something like perseverance, the specific risk that we're trying to mitigate the most is the technical risk. We are very sensitive to the cost risk. We are very sensitive to the schedule risk. Cost risk because we are taxpayer funded and we're very cognizant of that. We're a very, very tiny percentage of the national federal budget. We're like NASA overall is half of 1% of the federal budget, and JPL is a tiny fraction of that. But it's still, we want to be very cognizant and very careful with our taxpayer dollars because, you know, I'm a taxpayer. I don't want to waste my money. And then the schedule, we're also very careful about because, for example, Mars, you can only launch once every 2 years. If you miss it, you have to wait for 2 years. That's a huge problem. But for Perseverance specifically, the thing it was most sensitive to was technical risk. So when we're mapping out our processes and we're figuring out what's the highest priority thing for us to focus on, we're looking for gaps where it's less of a concern about the waste and more of a concern about what did we miss that might cause this thing to explode. For the helicopter, on the other hand, it was a lot more about the waste. Because it was technology demonstration, I think it met something like 80 or 90% of its mission requirements. If it took off and hovered once, it didn't even have to land successfully. It's a very different set of needs. So we were a lot less focused on the technical risk because by definition, it's taking a massive amount of technical risk. That's the goal.
Yeah, you know, that's interesting. So in value stream mapping, one thing we do is there's little process information boxes like below the process box. Okay, here's your process step, and then there's information on the cycle time, the change over time, number of operators, things like that. Is the plan when you're doing this is to have some sort of risk rating system or sort of color codes to show this is the super risky step or this is the non-risky step, or is there any way to pull that
in?
So
this is one of my main products, so I can talk about this for a long time. So I'll dig a little bit and then you tell me whether you want me to keep going into further detail or not.
Okay.
Yeah, if anyone has questions, I can stop at any time. If no one has questions, I can ramble forever. So for our big projects are really big, either they're expensive, they're highly complex, they're a high national priority, they're very visible, they're a big international project, basically everything involving the Mars rovers. We have a low risk tolerance on those. So we make sure that we enforce and make sure they follow our standard best practices. All the things that we built up over almost a century of work as an institution. We were founded in the 30s, right? We actually have been doing satellites since before NASA existed at JPL. So they follow every single best practice, and it's a lot of work, but boy, does it catch a lot of failures. Every single one of those rules, while annoying to follow, exists because there was one time we didn't and something broke. And so now we have a rule in every single one of those. Something like the Ingenuity helicopter that doesn't meet its needs. It's outside of its cost scope, it's outside of its schedule scope. The thing that for Ingenuity, if it wasn't ready to fly when Perseverance was ready to go, Perseverance was its ride. It had no way to get to Mars without Perseverance. It really, really, really needed to be ready when Perseverance was ready, more than it had to have an extra couple of days of lifespan and technical risk. So the way that we do it for the big projects is they have to follow every best practice. The way that we do it for some of our higher risk tolerance projects, so things that are technology demonstrations, where inherently the whole point is to take a massive risk, like the helicopter, or something that's easier to fix because maybe it's on the ISS and we can have an astronaut fix it if they need to. Whatever the reason is, we actually tailor our requirements for it. And so the process of tailoring is where things get funky. For the big projects, we don't let them tailor because anytime you start changing, messing with stuff, you're introducing possibilities for gaps. You're introducing a lot of risk because you could have a disconnect in the handoff. But these guys, it doesn't meet their requirements. They need something different. So we're going to meet their needs. We're going to actually tailor down to what they have. And that introduces some risk in terms of the handoffs. So what we try to do is I worked with dozens of subject matter experts from across our section and across the lab to actually define, okay, what stuff is the highest risk? What stuff is the lowest risk? Make sure we don't give away the farm, basically. I'll let you not do this, but I won't let you not do this. this thing is really big deal for technical risk, but not such a big deal for schedule risk, or vice versa. And I put together, I helped improve. We already had, we have a menu basically where we say you can you come to us, we'll work through this process with you with a bunch of hours of discussion to make sure we don't miss too much. And we'll say there's a gold, silver, and bronze level. And for your circuit boards, gold, silver, or bronze. For your thermal testing, gold, silver, or bronze. And we'll go through what are the levels we're willing to work with, what are we not willing to work with. And it's a lot of work to tailor it because you want to make sure you don't give away too much and accidentally destroy the thing, because we have a responsibility to make sure they meet their requirements. But you also want to let them meet their needs as much as possible, right? Like, I don't want to say, nope, I'm not willing to move at all, when realistically, understanding their specific needs and their specific challenges, yeah, this would make sense for them. And so it's really weird having these two different systems in place at JPL. It's something we're constantly improving and constantly navigating, but we work on it.
Oh, interesting. Yeah, I like that sort of, you know, gold, silver, bronze sort of scaling sort of thing. Because I think, you know, at the end of the day, although you got a big, massive technical problem, you're working with people that need a way to sort of conceptualize. And it's easier to say, you know, I'm working on a silver requirement as opposed to, you know, explaining all the technical details. Hey, Jordan, so we're at about, yeah, Chris?
Oh, I just had like a follow-up question to you, Jordan, just like kind of speaking on that, if I can. So do you ever have any like problems coordinating with people? I know engineers at JPL might want to push the boundaries and kind of QA might want to be drawing it back in a way. Do you have any specific examples of maybe when that happened and like a compromise or risk assessment that kind of solved that?
Yeah, so one of the many reasons that I say that QA at JPL is very much engineering, it's not just implementation, is because we're constantly doing these assessments and we're constantly doing it what we call the art of QA. Part of that is understanding which battles to pick. You're not going to do every single tiny little thing because A, nothing will ever get done because there's always something. And B, you're going to piss off every single person around you. And you're just going to hate yourself at the end of the day too. So it's understanding which battles to pick, which things are the biggest deal, which things are not that big of a deal. That's something that I'm still learning, especially because I'm, you know, only a year or two into being full-time here. I have a lot to learn in that area. Some of our more experienced people are very knowledgeable in that area. They still disagree, but they have a lot better skill with it. In terms of how to work with people, so one of the things at JPL, Dr. Olsen was right. We're very much an applied R&D. It's actually we're structured as a federally funded research and development center. It's called an FFRDC. It's in the name. We design things, and it's not just, hey, this was an interesting idea. It's cool. We just launched it into space. We're going to see how it works, and we're going to answer our questions that way. But every single project kind of has its own culture. And then there's also the JPL culture, and there's a lot of intermingling there. So certain projects, you know, like Helicopter is going to approach things very differently from how Perseverance approaches things, because they have a very different thing they're trying to achieve. On the Perseverance project, a lot of the engineers I worked with, this hardware was their baby. They were delighted when I found a tiny yellow spot of corrosion on one of their pieces of hardware so that they could then go spend the next day cleaning off the corrosion. They were delighted. Other ones I worked with, they were like, we don't want QA at all. On not for engineering specifically, but I'm not going to name names, right? But it depends on the needs, it depends on the culture, it varies widely. And so a lot of it is pairing the right quality assurance engineer with the project that meshes culture-wise, meshes personality-wise. A lot of it is QA is supposed to be the independent technical authority, so we're the checks and balances, right? We're one of the checks and balances. There's also other ones. So we're not supposed to go too deep into being with them. We are supposed to be a check and balance on them. So we're supposed to be part of the team, but also a check on the team. And it's weird to balance, you know, when do you say no? And when do you say I'm part of this team, and not just letting them convince you of everything, right? When to push back. It's a super vague answer because it differs wildly depending on what you're working on. But that is something that we are constantly navigating. That is one of the most important skill sets a QA engineer at JPL can have. And it really depends on the situation. And when you don't know what to do, that's when you start asking for help and you start getting consensus from lots of people.
Well, I think asking for help is sort of a key skill in any organization. And a lot of organizations, part of the problem is, asking for help means that you're surfacing a problem and you get squashed, for that, right? And trying to build a culture where it's okay to ask for help is sort of a code word for okay to surface problems and issues and hopefully resolve them. Hey, Jordan, I'm gonna have to sort of call it quits there. We've been doing this for like 40 minutes, but it's a great 40 minutes. I really appreciate it. Is there any parting piece of advice, or for these folks that are just starting on their lean journeys? You've been on your lean journey for a while now. Is there any parting piece of advice you want to provide for them?
Yeah, especially since this is a class of MBAs, right? So a lot of you might not be directly going to manufacturing where you're being lean practitioners on a daily level. As someone where lean mostly applies, but there's some weird ways I have to modify it, you folks will probably find something similar. So there's two things that I really took away from Lean Six Sigma, and it was one of the best things I did in college. I'm really glad that I studied it. One of them was this list of tools, right? It's like, how do I do a fishbone? We like cause networks a lot at JPL. I'm not going to get into that. Dr. Olsen knows I can get into that. But like, there's lots of different tools, like value stream mapping. You can get a book of 100 different specific tools you can do. But the thing that I took away a lot more from Lean was the mindset, was the idea of looking at a process to set something up for success instead of just trying to figure it out on the fly, in terms of preparation actually always being worth the investment. Every single time, it always saves you time, no matter how stressed you think you are. In terms of knowing when to ask for help, in terms of continuous improvement, in terms of knowing when to go reach for those tools you have, but knowing when to reach for it, not just immediately jumping for the solution. You have to go through DMAIC. You have to actually define the problems before you can try to solve them. And I rarely use strict DMAIC. We're doing it in a project I'm doing right now, but for the most part, I do kind of jump into stuff. But that mindset is applicable to everything. Sometimes you're going to go pull up a process flow diagram. Most of the time, I don't. Most of the time, it's just understanding when to go work with people, not using a specific Japanese word. And so I thought that was a really important thing that I took away from it. I would highly recommend passing on that mindset and just being open to trying to change things, trying to ask for help, and knowing when to reach for a solution instead of just immediately throwing a tool at the problem and saying, well, that'll fix it, when you don't even know what the problem is.
All right, Jordan, great advice. Thank you once again for being here. I didn't think, after the last time we did the celebrity interview that you would actually know more the next time. But sounds like you're doing some really cool stuff, and thanks for being there, and thanks for sticking with it. So, okay.
I appreciate it. Anytime, I'm always happy to.